we're looking at 16, 30, and we wanted to look at 36, I think, correct? All right, so let's start with question 16. Question 16 looks just very similar to one that we did in class, actually. It is a pentagon, not a regular pentagon, so I'm going to try my best to draw it, but I mean, it's not going to be perfect. This is 100, this is X, this was 115, 105, and 117 up here. Okay, how do I answer this question? We did one almost identical to it in the notes last class. What do we do? What am I looking for first? I know I'm trying to solve for X, but how do I solve for X, I guess? What would I do? I know you know. Deshay, what'd you do? Okay, I'm trying to find the sum of all of the angles inside of that shape. How do I do that? How do I find the sum? What is the sum? I know it's supposed to be something. What is it supposed to be? How do I figure that out? You said 540? How'd you get that? So the sum of the interior angles is 180 times n minus 2, right? Did we use that formula last class? Okay, how many sides does this have? 5, so this is 180 times 5 minus 2, or 180 times 3, and that's 540, right? So I'm going to write an equation. It's going to be 105 plus 115 plus 117 plus 100 plus x is equal to 540. Now, some of you might not have written that whole thing out, and you might have just added them all up first. That's fine, and then subtracted from 540. The reason I continue to do it this way is because sometimes, and I have seen it on the SOL, where the answers that are the angles up here are all in terms of x. So you would have to write a big equation. Okay? So when you go ahead and solve this, you're going to add the current things that you have together. So you'll add the 100 and combine like terms. So 105 plus 115 plus 117 plus 100. Oops. So you get 437 plus x is equal to 540. And then you're just going to subtract the 437 from both sides. Okay? And you get 103. Okay. Is that okay? Good. All right, then let's look at 30. Okay. Question 30 says, ooh, that was pretty. Let's look at this one. So this one, we have, I'm not even sure how to draw this. I'll have to extend it at the end. So we have a triangle. Really, Ms. Meckert? Helps if I can draw a triangle. We have a triangle. I think this is the extended side here. And we have a bunch of exterior angles. Let me just draw what we know. So we know that this is x, y, w. And this is z minus 13, z, and z plus 10. Ooh. All right. That was a toughie. Don't you agree? This is actually going to require a system of equations. No wonder it was hard algebraically for you. Okay, I get it. This would definitely be something that would be a challenge type problem on a test or a quiz. Okay, this was a doozy. All right, so we know a lot of things. Okay, I know that y, I'm just going to write everything that I know. I know that y plus z plus 10 is equal to 180. Would you agree with that? Just a linear pair, right? I know that z plus x, I'm going to write it a little bit differently here. Okay, and I would be glad to, let me just write down my stuff and I'll be glad to do your way, okay? So z plus x is 180, and then I have this, I have w plus z minus 13 equals 180. And then don't I also know that w, x, y, I'm sorry, x, w, and y add up to 180 also? What is the problem with all of those things? Can I solve any of them for x or any of them for y? Not the way they're written, okay? So Marvin, you want to help us out with a direction here? What'd you do?
In your case?
Huh?
In your case, the way you're doing it.
No, in your way. You can do it a different way. Give me a different approach, because
Okay,
that doesn't work.
Because the way I did it is that, that I call the exterior angles are 360, so you couldn't add them up.
Yeah, that's exactly right. Not 160, they're 360. That's what you meant to say. That's what you meant to say. But my point is that when you're struggling on a problem, right, and you're looking at what to do, you can notice the linear pairs, right? You notice all the interior angles, but then, and you have all these equations that aren't really helpful because we'd have to do a system of equations. But what Marvin's suggesting is that if you look here and you only look at just the exterior angles, is there a relationship or an equation I can write just for those? Sure. What does all of the exterior angles have to add up to be? Okay, so let's try that equation first, okay? So let's do that. So z minus 13 plus z plus 10 plus z is equal to 360. That'll at least we can solve for z. Would you agree? Once I figure that out, then maybe I can come up here and figure out some of the others. Fair enough? So let's find z. Okay. So how many z's do we have? We have 3 of them. So 3z plus, actually I guess it's minus 3, isn't it? Just combining like terms here. Minus 3 is equal to 360. Subtracting 3. What is 357 divided by 3? What did I do wrong? Oh, 363 divided by 3, what's that? What'd you get? 129. I've got to talk louder. Okay, 121. Good. All right, so that's one of the variables, but I still have to go and find the rest of them, don't I? So I could plug them in. Well, I could replace this guy with the 121. Would you agree? And then what would x have to be? What's 180 minus 121?
59.
Okay, so 59. So x is 59. We're still looking for y and w. Well, could I plug in a 121 here to find w? Right? So if 121 minus 13, and then I'm going to subtract that from 180, and I should get w as 72. I agree. And then we still want to find y. I could go ahead and replace 59 in here, and I could replace 72 in here and figure out what y is. So the key is that these equations were helpful, but only after we knew what z was first. Okay, so you had to do the yellow highlighted stuff first. What did y end up being, by the way? Okay. Good. I thought that was a good problem. Awesome. Lots of things to think about. Okay, and then the last one you guys wanted to look at was 38. 36 or 38? I keep thinking the wrong number, sorry. All right, 36. So in 36 it says the measure of an exterior angle of a regular polygon is given, and in this case it was given as x. That's going to be the exterior angle, okay? It asks for an interior angle, and it asks for the number of sides. So obviously in this case, we're going to have to do it in terms of x. We're going to have to write x in our equation. How does the interior and exterior angles relate to one another? They're supplementary, right? They add up to 180. So if I know the exterior is x, how do I find the interior? Isn't it just 180 minus x? Subtract it from 180, right? And that's would give you the answer for the interior. To find the number of sides, wouldn't it just be the total of the sum of the angles of the exterior angles divided by an exterior angle? Those are just the formulas. That's all it was looking for there. Okay? That's all it wanted. All right. Go ahead and put that away for me for now. Okay? I am going to ask for a member of each table to do me a favor and come up and pick up one of these bags. We're going to do a little work with what's called tessellations. And these are like I don't even know. These are shapes that they click together. So I'm going to go ahead and pause the recording for a minute. Just send somebody up, a representative, to come get one of these. Who knows what a tessellation is? If I say the word tessellate, what does that mean? I'll give you an example of what a tessellation is. The tile floor in our classroom is a tessellation. Matter of fact, any tiling is considered a tessellation. Like if you have a tile in your bathroom, or if you have tile. You ever go like underneath an overpass and you see the patterned walls underneath like the concrete? Those are tessellations. Give me so let's decide what a tessellation is. What is a tessellation? There is symmetry within tessellations, absolutely, and we'll talk more about that in the upcoming weeks. But what is a tessellation? Look at the tile floor. What makes it a tessellation? The shapes fit together. Perfect. And how do they fit together? Are there any gaps? No. Okay? So a tessellation is simply when you have a shape that repeats in a pattern, right? It repeats in a pattern, and it's a shape that covers a plane. Remember what a plane is, a flat surface, okay, without any gaps. So a shape that repeats and covers a plane with no. So hang on one second. You probably should, and you're going to need notes in a few minutes. We are going to use these tiles in just a minute, okay? Today's notes are always titled up there, Tessellations and Area of Regular Polygons. Area of Regular Polygons. And today is April, I'm hoping it's April. It is March 18th. You're welcome. All right, so right now we're going to be working with just the regular polygons. And if you look in your bag of things here, we are, and I know that yes, and I knew someone was going to do it, they do make 3D shapes, and we will eventually use these to make 3D shapes in about after spring break when we do our 3D unit. But right now we're only dealing with flat surfaces, so please do not create 3D shapes today, okay? And we're only going to be dealing with regular polygons, so you're going to have to eliminate some of those choices in your bags. This shape up here that I'm holding, this, I guess it's an isosceles triangle, not worried about that one right now. So kind of put that back in your bag. Okay? So do me a favor and sort through all of the figures in your bag and only deal with the regular polygons that are in your bag right now. So take a second to sort through them and figure out which ones we're dealing with. So you guys can just put the non-regular ones back in this tub, okay? So I want you to investigate, and this is an SOL question, okay? So it's something that you absolutely should write down once we do our investigation, okay? But which one of these, and I'll go ahead, which one of these regular polygons tessellate? And I'm going to go ahead and eliminate this one since we don't have, well, I'll leave it there. But we can investigate with just the first 4, because those are the shapes you have, right? Which one of these regular polygons tessellate? There will be more than one answer. This is an SOL question that would say select all that tessellate. So you're going to have to pick which ones tessellate and which ones don't. So you have the tools. You can't use these on the SOL. Okay, so you have to, this is our discovery idea. So pick a couple, someone on each table. Someone can work on the square. Someone can work on the triangle. Someone can work on the pentagon. And decide which ones tessellate. I want you to come up with your ideas on your own table, okay? Which ones tessellate and which ones don't. So I agree with your answers so far. And I think, Marvin, if you show me your thing, this is a good example using our manipulatives here, that there is a gap with the pentagons, right? So they don't actually by themselves tessellate a plane. There would be a gap here. So they would not be a good tile to use. But the hexagons, I think it was Jason over here had a good tessellation of the hexagons. Notice there are no gaps. You could continue and they would kind of cover the entire plane without any gaps. That's great. I see over here the squares, just like the tile floor that we're stepping on, also tessellate the plane. And then the triangles. Who had the triangles? Yeah, you guys had well, you put it all together. But you're making cute hexagons with the triangles, but you can kind of see that they do tessellate the plane, and you can continue on in all directions. So equilateral triangles work, hexagons work, squares work. The pentagons we know for a fact do not work. Okay? And what about octagons? Well, since we don't have an octagon tile or an octagon thing, let's go ahead and figure out if we can mathematically discover why pentagons don't and why the others do. And then let's make a hypothesis, or let's make a decision about what we think about the octagon. Okay? So do me a favor and put the things back in your bags for me. Okay? So you guys can put them right back in this bag, please. Thank you. So put everything back in the bag. Bring it up to me. So I'm just going to kind of, let's make it bigger. I'm going to just use a highlighter just to make sure that we know for a fact that this is our select tool. This one and what I'm highlighting does in fact work. We just proved it with our manipulative tiles that we had. Why do these work? It has to do with the interior angles of the polygon. Anybody care to make a conjecture, an educated guess, as to why those do and the pentagon does not? Has to do with the interior. Let's find the interior angles first. What's an interior angle of a 60, okay? And then how about 90, okay? How about the pentagon? $72. No, it's not 72. It's 108. What's that? So it's 108. Okay? Thank you. Who is this for? Mr. Bird. Okay. Mr. Bird knows in trouble. Okay. And then what about in the hexagon? Third floor office? You know what that is? Here, I'll show you. Interior angle of a hexagon. What is it? 120. All right. So why do the ones in yellow work and the one that's not in yellow not work? That makes any sense? Yes. Not by 30, but by 360. They all go into 360. That's exactly what it is. So they're all divisible by 360. Why does that even work? Let's think for a second about the tessellation. Let me just kind of see if I can get one real quick. I should have kept y'all, have y'all keep one together, but I didn't. Of course, I pick a small one. Goofy. Sorry, give me a second, y'all. I'll be back. Why am I worried about 360? Where did the 360 come from, I guess is my question. Now the exteriors, again, look at this that I've shaped. Look at all of these interior angles that form a what when they are all put together? A circle, right? And so there's no gaps. So that means it's all 360 right here. And that will work for any corner of the polygons, okay? So we're going to take this idea, okay, and apply it to, what about an 8-sided figure? Will it tessellate? We don't have a shape to play with, but we can make a decision. So I want you to decide. Tell me yes or no. Does it tessellate and why? You said no. Already made a decision. No. You know why? Why are there gaps? The answer is no. Why is the answer no? It doesn't work. What's the same process that I did with the interior angles? What's the interior angle of an octagon? 135. Is 135 divisible by 360? No, that's why it doesn't work. That's why there would be gaps. Okay? So if we had a bunch of octagons, they wouldn't fit together for that reason. Fair enough? So again, if you had this question on the SOL, could you answer it? It is one of those where you have to select all, and if you miss one, the whole question's wrong. Okay? So we can either memorize it, or you can look at the process of the interior angles. Fair enough? All right, one more question about tessellations. Will these two regular polygons tessellate, forming a semi-regular tessellation? Meaning if I put the two together, will it work? Okay? So what do you think? So let me show you what I mean. If I took literally this guy here, and I rotated it, and I kind of tried to make it so, well, let's first of all make it so it's the same size. And I tried to make a tessellation. Could I make a tile pattern with these two with no gaps, do you think? Try it. Go ahead and get in your bag and go ahead and get a square and a triangle. Try a couple and see if it works. Does this work? Okay? How about a pentagon and an octagon? I'm sorry, a pentagon and a hexagon. Would that work? Okay? Could we try this one? Tell me what you think. Okay? Which ones will work, which ones won't? Does a triangle and a square work? I could fit a triangle in here, but then two triangles will be next to each other. I don't think it does. Does it continue to work when you continue on? Hold yours up, Deshay. Oh, but yes, and so you would need a third shape on the inside. You would need. So let me show you Marvin's. Marvin's got a good pattern here. I don't mean to take that away from you. Okay. If you kind of alternate and go around in a circle, what's going to end up being in the middle? I think it would be a hexagon. Can you see that half a hexagon here in his shape? And the hexagon would be formed by the triangles. I mean, in theory, that would work. But it would still be it would be three shapes, wouldn't it? A hexagon, a square, and a triangle would work. Would you agree with that? So, okay, here's a different option, okay, where we could kind of create, she's actually creating almost a square-like pattern here, a rectangle-like pattern here with the triangles. Okay, so sort of tessellate. Would you agree with that part? Okay, so we can manipulate them in ways to make it work. However, which ones definitely don't? Right? Would you agree with this? There's no way to get this to work. Okay? So your job right now is to figure out what only two shapes now. Only two. Can you come up with, I'm going to give you probably about 3 minutes. That's all the time we're going to have. Can you come up with two that will tessellate, two regular polygons? So we said a hexagon and a triangle. And they need to be regular. That will work. All right. All right, so we are going to spend the rest of class today talking about area of regular polygons. And if you do your research, like I know Marvin will, he'll go up and he'll do some research for me. There are formulas that you can memorize for finding area of polygons. But I'm not a big fan of memorizing formulas, so I'm going to show you how to do it without formulas. Okay? Yes, exactly. Okay? There's something called an apothem, but we're not going to even talk about what that is. I don't care. Okay? Huh? Apothem, A-P-O-T-H-E-M. Okay, that is a different way to find the area. Thank you, dear. But not what I'm looking for. Okay, it's not a formula that's on your formula sheet. So the only way that I would be able to help you, or you would be able to solve it using what you're given on the SOL, would be to do it using this method. So what we're going to do is we're going to actually take all of the polygons that we have and we're going to divide them into triangles. So take your hexagon and we're literally going to divide them into triangles. So I want you to do this too. If you want to use the ruler that I gave you for a Valentine's Day, or you want to borrow a ruler, that's fine too. You want to just draw your sketch, I'm fine with that. Okay? So go ahead and divide it up. And I want you to tell me what's true about all of those. It probably doesn't look that way with the picture looks a little, I think it's the screen resolution, but it might not look to scale, but it is. But what is true about all those rectangles? Triangles. Thank you. What's true about them? They're all what? They're all congruent to each other. All the triangles are congruent. Now, all the angles together, the top form 360. I agree, and we're going to use that in a minute. So let's take one of them, and if I can find the area of one of the triangles, can't I just multiply it by 6 and get the answer? Doesn't that seem reasonable? Okay, so we're going to find the area of one triangle. So I'm going to draw it off to the side. Okay, and I'm given some information about the base of that triangle. It's 6. You agree? Yes, no, maybe so? So how do I find the area of a triangle? There's actually 2 formulas. One you've already heard of, one you probably haven't. The first formula is 1/2 base times height. I know you've heard that formula before, right? 1/2 base times height. So we'll start with this method. There is another formula using the sign. We'll talk about in a minute, okay? What's the base in my picture? Sticks. I agree. Do I know the height? I don't, but can I find it? You can. So what I'm going to have you do is, this is the height. Would you agree? Well, let's try to draw it like an equilateral triangle in this method. So, well, you know what I'm going to do? It's actually not equilateral, it's isosceles, but let's draw it as an isosceles triangle. Okay. And then I will draw in, I wonder if it'll let me draw it red. No, probably not. Draw in the height. So I know that this whole thing is, can I just make it 3 and 3? Is that okay with you guys? Don't I know that that height breaks the bottom in half if it's an isosceles triangle? How do I know it's isosceles, by the way?
Because you're going from one angle to the center, and the angle is in the same.
That's not why. Why is it isosceles? Look at it. Look at the triangle, how it fits in the hexagon. Why is it isosceles? Why is this distance the same as this distance? Well, they're going from the center out to what's called a vertex. We call that a radius. If this was a circle and this was inscribed inside the circle, wouldn't that be the radius of the circle? We also call it a radius of the hexagon. Okay? And since they both have the same radius, we know that it's an isosceles triangle. Okay. What other information can I gather from, what other information do I know? I know something else, believe it or not, in the triangle. And it has to do with what you were saying when you walked in, Gabriel. What other information do I know? Do I know another side length? No. Do I know any angle measures? Yes. How do I know some angle measures in this triangle? Say it louder. Okay, I do know that it's 90, I agree, but I'm talking about some of the other angles. You know, Julian? I'll come to you. How do you know that? I know what he's thinking. Do you have a different thing to say, or is that what you were going to say? How do you know that? Well, that would be for an equilateral triangle, is the 60, and not all isosceles, but you're on the right track. Okay, keep going.
The thing is because, like we have
Yes. It happens to be 60 degrees here, but not always, okay? So yes, that's what I was thinking. If you look here, and it happens to work for what you're saying too, but be careful with your method. All these angles, the top corners of all the triangles, don't they all fit and tessellate in a way? So isn't each of these top angles just 360 divided by 6? So isn't this up here 60 degrees? Well, doesn't that mean that this is 30 degrees and this is 30? It happens that it's 60 here, but it's not always, okay, just because it's a hexagon. So do I have a 30, 60, 90 triangle? I know some stuff about 30, 60, 90 triangles, y'all. What do I know? I want to find this height, don't I? Because that's the height of my triangle. How do I do it? Do I have the short side? I do have the short side. I'm not doubling it. 3 radical. 3 radical what? 3 radical what? Come on. 3 radical 3. Okay? 3 radical 3 is going to be the height because it's radical 3 times the short side. Remember this from special right triangles? If we didn't remember that, could we use trig? Could we say that it would be the tangent of 60 is x over 3? That's okay. I don't care that you did exact. I'm not looking for an exact answer here. Okay? So round it if you need to. But the height is 3 radical 3. Now that's the area of one of the triangles. How many triangles do I need? 6. So I'm going to go ahead and make sure. Whoa, where did my 1/2 go? Really? I'm going to put my 1/2. That's 1/2 base times height. And then I have 6 of them, don't I? Because there's 6 triangles total. So tell me what the area of the hexagon is going to be. Look at all these worlds colliding, special right triangles, properties of isosceles triangles. We need to know that things tessellate. Oh, big picture. So 6 1/2 base times height. What'd you get? Give me a decimal, that's okay. 93.5? I got that too. Not exactly, like 93.53? Okay. So 93.53. And if we're going to say units, whatever those units are, oh, centimeters, right? So centimeters, really, Miss Mackert, I have the biggest eraser on right now. It would be centimeters squared for area units. Would you agree with that? Okay. How do we feel? It's all about dividing your figure into congruent triangles and then trying to figure out the measurements that would be missing. Okay? Let's try another one. Okay? It's a little bit different. Can we find the area of this triangle? Where the dot in the middle happens to be the center of the figure. I might draw up this example into your notes as well, because this is one you're going to see for homework, or similar for homework. What is the 6? Is it a base? Is it a height? Is it neither of those things? It's part of the height. It's not half of the height. Be careful with that. Let's divide it up, shall we? Okay, let's divide it up into triangles. So what I mean is this. Let's take and draw in the radii. The radii go from the center to the vertex. Okay? When you draw in the radii, we've now divided it into 3 congruent triangles. Notice where the picture goes, or where the radii go, from the center to the corner. That 6 is not a radius, like it was in the last picture. Do you agree? In the hexagon, the 6 was a radius. This is not. But if I find the measure of one of those triangles, how many would I have to multiply by to get the whole thing? 3. Okay, that's good. So once I've drawn in my radii, I'm just going to draw the separate triangle over here, just so I have some room to work. What do you think? Do I know any other side measurements at all? No. Do I know any other angle measurements at all? Yes. How can I find an angle measure? Same way I did before. If I look at the inside here, what does that top angle of the big triangle have to be? 360 divided by 3. And what is that? Good. So the whole top up here is 120, but it's now cut in 2, so it's really 60. Do you agree? And say what? Where did I get that? Because if I look at this peace sign over here that I've drawn in the middle, I have 1, 2, 3, and they all have to add up to 360. So this whole angle down here is 120, and then half of that. Okay. So now I'm just going to look at this 1/2 base times height. I have the height of this triangle, but don't I need the base? Don't I need this guy down here? Right? So I'm given the 30. I'm given the short side. How do I find the long side? It's the short side times radical 3. Well, I want the whole thing, because I have 3 of these guys. So I have 3 1/2 base times the height. The height is 6. What's the base? The whole base. If half of it's 6 radical 3, what's the whole thing? 12 radical 3. Because this would be 6 radical 3 also, wouldn't it? So if I added those together, it's 12 radical 3. Mm-hmm.
In the 330, 60,
Mm-hmm.
6 is the bottom, so wouldn't it be...
No, 6 is not the bottom. 6 is the height. Notice where 6 is. 6 was here.
I mean, here, wait a minute.
6 was here, so 6 is here.
Yes, so wouldn't that be the bottom of the, this is the hypotenuse, right?
Right.
So this would be 6 divided by...
No, that's given
Sorry,
to me.
oh.
That's given to me. And the problem is 6.
Yes, I know, but if you're looking for half of
I'm
it...
looking for half of that. I'm looking for this.
I know.
This is the short side. The long side is radical 3 times that.
I think about this moment.
Did I do something wrong? Now I'm questioning myself, because Marvin's always right. Did I do okay? No? Yes?
Go on,
All right, Marvin. Marvin's always right, so it could be wrong. I think I'm right. I've done this for 20 years. Maybe I'm wrong. Could be right. Okay. Anyway, so here we go. So tell me the area. Go ahead and plug it into your calculator. Tell me what you get. And if this thing doesn't stop being so ginormous, we'll be all right. So 1/2 base times height. There we go. Tell me what the area of the whole figure is. Put the 1/2 in parentheses. And it might not matter in this case, but I want you to always get into the habit of doing that. Sometimes it does matter, okay? So be careful with that too, okay? Put your 1/2 in parentheses.
You're right.
I know. That's okay though. But thank you for, hey, make sure you're asking. I'm proud of you for doing that. Did you get an answer? Put your 1/2 in parentheses, folks, when you plug it into your calculator, because it's a fraction, okay? So make sure that you're doing that, because if you don't, the calculator sometimes will give you the incorrect answer. Or you can use 0.5. I'm cool with that too. Anyone get an answer yet? I'll plug it in with you. I got 187.06. Does that look right? That's okay to do decimals, and that would be centimeters squared here as well. Okay? Anyone not get that when they plugged it in? Brittany, you got that? Good. All right, let's do one more. Okay? One more. Not that one. Let's do this one. Yes. Did you not get that when you plugged it in? So homework pass on this problem. The only information I'm giving you is that the side lengths are 12. Okay? And so if you come back with a completed solution, make sure you do it on another sheet of paper. We'll go ahead and do a homework pass. They will be due at the beginning of class on Friday because we will go over this at the beginning of class on Friday. So you'll need to turn it in for me if you want that homework pass at the beginning. Okay? Fair enough? Okay. So what your homework is going to, oh, by the way, can we go back really quick? I'll let you write this down in just a minute if you have a question. But what was kind of the process to both of these problems in solving the polygons? What did I always have to do first? Divide it up into triangles. Even if the original problem was a triangle, right? I still had to divide it up. Do you agree? So I did that by drawing in the radii. Do you agree? Over here, from the center to each of the corners, I drew those in. And then I picked one of the triangles and tried to solve it, to find the area of it. Okay, so that's the process. All right, let me go ahead and give you your homework. I'll write it on the homework pass problem. Okay, it's going to be on two different pages. It's going to be on 600 and 601 is the first part. And I'm going to have you do problems 31 and 32. And problems, I don't know. I'm going to do 43 through 52. And that is a Venn diagram, this 43 through 52. They give you the Venn diagram, and all you have to do is put the words in the Venn diagram. So each word is a problem. So it looks like it's a lot, but it's really not, if that makes any sense. Okay? So 43 through 52 is a Venn diagram problem. And then I'm going to go ahead and give you some homework problems on area of polygons as well. In a minute. You tired, Jason? I get it. I'm tired too. Maybe I am, and maybe I'm not. There we go. Nope, that's not it. Good grief. All right, and then it's going to be on page 632. And I'm going to have you guys do 21, 22, and 38. Okay? And then you had the homework pass problem as well. Okay? There you go.